병원에도 특히 관심이 많을 텐데, 일본에서 중이타 치료를 많이 하고 계신 그런 교수님을 모셨고, 간단하게 교수님 먼저 소개드리면, 무츠미 타시로 교수님이시고, 그 오사카 유니버시티에서 박사 학위를 받으셨고, 그리고 2000년도부터 오사카 유니버시티에서 또 연구를 하고 계시다가 2004년도에 군마 유니버시티로 와서 조교수 하시다가 지금 이제 최근에는 23년부터는 교수로 근무를 하고 계십니다. 그리고 이제 주로 관심 있는 연구는 매니지먼트 오브 카본 아이온 테라피 시스템 패실리티, 그리고 리스퍼레이션 모션 매니지먼트, 입자 치료에서 모션 매니지먼트, 또 오토매틱 페이션트 포지셔닝 시스템, 이런 것들, 스몰 사이즈 카본 아이온 디벨롭먼트 해주시면 그런 쪽에 많은 연구를 하고 계시고, 주로 오늘 이제 카본 테라피에 관해서, 사실은 우리나라는 이제 막 시작하는 입장이지만, 전 세계적으로 일본이 카본 테라피는 가장 많이 환자 치료를 많이 했고, 또 경험도 많고, 또 거기서 어떤 일을 하고 계신지 그런 것에 대해서 발표를 해줄 거고, 여러분들 잘 듣고 또 궁금한 거 있으면 이런 기회가 흔치가 않아. 그래서 중이타 치료 관련해서 궁금한 거 있으면 많이 질문해 주기 바랍니다. 큰 박수로.
Good afternoon. I'm TASHIRO from Gunma University. So I'd like to thank Professor Min to invite me here, and I'm very happy to present my research and introduce my research and facility here. So I'd like to introduce my facility, Gunma University Heavy Ion Medical Center, and the medical physics research, one of the medical physics research. So this is my self-introduction already. My specialty is medical physics and particle therapy physics. And I like skiing and mountain climbing like this. And the outline is introduction of carbon ion beam cancer therapy, because somebody do not aware about the carbon ion therapy, so I will introduce this carbon ion cancer therapy. And also I will introduce our facility, GHMC facility, and irradiation system. And then I will show medical physics research, especially about the system development for ultra high dose rate carbon flash irradiation, and also show some biology results. First is the carbon ion beam cancer therapy. So this graph shows cause of death in Japan. This red curve is cancer. So since 1980, cause of death in Japan, the cancer is number one. And I also checked the internet, so I found this causes of death in Japan and Korea comparison. So the situation is similar also in Korea. This is, sorry, Japanese slide, but this green one is the cancer. So the treatment of cancer is a very important issue in Japan and also in Korea. So radiation therapy is one of the choice of cancer therapy treatment, and conventionally X-rays, gamma rays, and electrons are used for cancer treatment. And nowadays also proton and heavier ions such as carbon ions are also used for treatment. The proton or carbon ions has a advantage of this. This is depth dose distribution, and the proton and carbon ions, heavy ions, has this peak. This is called Bragg peak. So if tumor is located here, dose concentration is possible compared to X-ray or gamma rays. So another advantage of carbon ions is lateral scattering. Compared to protons, multiple Coulomb scattering is less for carbon ions than protons. So in deeper positions, carbon ions, dose distribution is sharper. So it's also the advantage of carbon ions. This is a comparison of the dose distribution of X-rays and carbon ion beams. So X-rays is like exponential. So in carbon ions, this Bragg peak can be spread by changing the incident energy, carbon energy. So we can make SOBP like this. So those for surrounding normal tissue can be reduced. This is the advantage of carbon ions and also proton. And this is also comparison of the X-ray treatment plan and carbon ion treatment plan. Those coverage is similar, but the dose of surrounding normal tissue can be smaller. And this is also the comparison of liver case, X-ray and carbon ions. And another advantage of carbon ions is the high LET, linear energy transfer. So it makes the different biological effect. For example, this curve is a survival curve. Dose and survival fraction, and high LET beam shows this like this. So in the same dose, the survival fraction is smaller than the lower, and the proton is like this. So this shows clinical depth dose distribution, clinically used. So physical dose is like this, but the same dose, but the effect is more. So this clinical dose is almost X-ray effective dose is like this. So we use this beam. This shows a simulation of the dose delivery in micro areas. So this proton beam and carbon ion beam, and these lines shows secondary electrons. So this is the ion track. So carbon ions makes more dense ionization. And this shows differences in local dose distribution for an average dose of 2 gray. And this area is 10 micron. It's like cell nucleus type. So this is a photon, X-ray, or 2 gray. In this case, 2 gray distribution. But carbon ions case, 2 gray, but some track, carbon track, it's very high dose is deposited. For 15 mV per nucleon, for 200 mV per nucleon, and this is 1 mV per nucleon. This is very near to the Bragg peak. In this case, only 6 carbon ion track makes 2 gray here. So this and this is very different. So we can expect a different biological effect of carbon ion and X-rays. This shows this is nucleus, and this green is shows the double strand break of the DNA. So this is X-ray case, and this is a heavy ions case. So heavy ions makes double strand break along the ion track. So the number of such double strand break is more in heavy ions. In this case, Fe ions is used. But this higher LET makes more double strand break. Double strand break is very important to make lethal damage to cells. So this is a difference of X-ray and carbon ion, heavy ions. How advantage is short course treatment. So conventional X-ray therapy takes 30 to 35 fractions. It takes 6 to 7 weeks. But in carbon ion therapy, the duration becomes maximum 4 weeks. Short 1 day. This treatment course is used in Japan, maybe and also in Korea. So very short time treatment is possible. It's also the advantage, especially for patients. This shows the carbon ion therapy facilities in Japan. There are now 7 facilities, and I'm in Gunma here. This Gunma is located almost 100 kilometers north from Tokyo. Tokyo is here. Then in worldwide, this shows the carbon ion facilities. So Japan or East Asia and Europe is the main area. And nowadays, China and Korea, the facilities are increasing. And also North America, now, facility now, they are building. So in Seoul, this is the Yonsei University Hospital carbon facility. They started treatment maybe a few years ago. And in Busan, Seoul National University is now building the facility. So including proton beam facility, there are much more facilities in Japan, but unknown in the world. So East Asia and Europe and North America is the main areas. So this information is a little older, but you can check the TTCOG website about this facilities. Okay, then I would like to introduce our facility and the irradiation system. Our facility, the construction started in 2007, and like this. And the first treatment started in 2010 March, almost 15 years ago. And as of now, we treated more than 3,700 patients. And this shows our facility. So we use carbon ions and ion source here, and linear accelerator here, and synchrotron, the 20-meter diameter synchrotron. And we have 3 treatment rooms, A, B, and C. A has a horizontal beamline, B has a horizontal and vertical beamline, and C has a vertical beamline. And also we have room D, and room D is not used for clinical, And this room is used for experiments and have a scanning beamform and used for physics and biology experiments. And there are some CT rooms for for treatment planning CT. And also we installed the in-room CT in the treatment room to verify the patient anatomical structures just before the treatment. This shows the beam delivery system. We use so-called passive beam irradiation method using the bubbling magnet and scatter and rich filter to make spreader and black peak and MFC multi collimator and range compensators. This is a basic illustration for make a uniform dose distribution. So bubbling magnet X and Y and scatter makes the uniform lateral dose in the patient position, and this being collimated by MLCE according to the shape of the target. Also, we are using spiral wobbling. In this case, we can reduce the scatter thickness, so we can along the beam range. This shows the illustration of simulation of uniform field formation. And this shows the treatment flow. Anyway, first we prepare the fixation devices because carbon ions dose distribution is very sharp. So the positional reproducibility is very important. So we use thicker fixation devices than that for X-rays. And we take the CT and we make a treatment plan. Then this plan is reviewed in the conference. Then after that we prepared the irradiation, the calibration measurements and the range compensator. Then axial irradiation done. This shows the weekly operation schedule. Normally we are treating from Tuesday to Friday, daytime, and Monday is used for maintenance, and Thursday evening and Saturday and Sunday is used for the research. Mainly, the treatment is mainly high priority. And there are many kinds of staff, like medical doctor, nurse, operation technologist, and medical physicist. I'm here, and also operators and dosimetrists. This is a photo of the treatment. In this case, lung treatment. Lung treatment, 4 fractions. We use 4 fractions, 4 pots. So one day, day 2, day 1, day 2, day 3, day 4. And we have fixed beam time. We don't have a rotating gantry, so we use the rotating patient like this. And also, according to the location of the tumor, we use spine and prone position also. Also, we use respiratory gating technique. Many particle therapy facilities uses this gating technique to reduce the field size to avoid the normal tissue loss. And also we installed the in-room CT because treatment planning CT is taken 2 to 3 weeks before the actual treatment. So patient anatomical condition can change. So if a medical doctor wants to confirm the anatomy and dose distribution just before the treatment, we take the in-room CT and we confirm the dose distribution. In this case, actually, the day of the treatment, some motion occurs even in the same respiratory phase. So in that case, we need to take sampling. So such daily anatomical change is a very important issue. So nowadays, adaptive therapy is a topic issue in X-ray treatment also. And particle beam therapy is also, this is a problem. So the online adaptive therapy is required, but it needs many technical development. So this is now on the research and development stage. This shows some treatment example. This is the bone soft tissue tumors. Upper side is the before treatment, lower is the after treatment. So, and this is head and neck tumors before and after treatment. And this is lung before and after treatment. So this shows the number of patients of Gunma University increasing, and now maybe almost 8,000 patients are treated. And this shows the cancer sites. The prostate is the most, more than 60%. And the other is like this. We are treating a variety of tumors. And nowadays, from 2016, national insurance covered some of the tumors. So nowadays, almost more than 90% patients are treated by the national insurance. Then I'd like to show one of the topic of medical physics research. This shows our medical physics group doing a variety of subjects. But, so these subjects are mainly for the advanced, highly accurate heavy ion beam therapy irradiation techniques. But now I would like to show this one, carbon knife irradiation technique and flash irradiation system. So Room D has a scanning beam. So we developed carbon knife system to irradiate very small target, like a small animals. So, for example, like this. And we make very small beam. And this shows a reconstructed dose distribution, lateral dose distribution. And this small size beam, we can get a very high dose rate in the center area. So we use this kind of beam for flash experiments. So this shows the flash, non-flash, conventional and flash beam we increase and we reduce the time of the beam extraction from synchrotron. So it takes maybe 10 spheres to achieve 10 gray. 10 gray, yes. But just one shot, like a flash, it achieved 10 gray. So we prepare some irradiation conditions and use this system for biology experiments. For example, normal, this field means extracted beam structure from synchrotron, and we reduce the time. Also, we increase injection number of carbon ions injected into synchrotron. So we get the higher intensity, and we use this position to irradiate the target. And we prepare some irradiation conditions according to the biology group requirements. And also, for such experiments, the measurement, those estimation measurement is important. So we examine the dose monitor and also ionization chamber. This is for voltage dependent of dose monitor. So we are using this voltage. So we confirm the almost flat response of dose monitor. And also we use the advanced focus chamber for the dosimetry. And so we estimated the recombination coefficient. So it's shown here. Even in very high dose rate irradiation, advanced Marcus chamber shows very stable recombination coefficient. In this case, almost 3%. So this is almost negligible for biology experiment. So we use this advanced Marcus chamber to measure the dose. So I would like to summary. We have 15 years experience in carbon ion cancer treatment and operation. And metaphysics studies for carbon ion therapy are ongoing, and system development for flash carbon research. And flash carbon depends on various factors such as dose, rate, environment. So we need to more data. We need to examine more things. So we expect future developments to clarify the. So thank you for your attention.